So I am recording the session, and let me share you the screen. Just a minute. Okay, so up to now, you can see that on Moodle, I have delivered the course contents and videos about first order and some parts of the second order differential equations. So here you have the topic on topic 2, okay? So the material which you have on Moodle is lecture slides for the topic number 2, second order ordinary differential equations. And then under the second order differential equations, we have cover different topics. So for example, the first topic was the reduction of order method. Its video is available, okay? The second, another topic is the Euler-Cauchy equations. So some videos for the Euler-Cauchy equations are available there. And then some more videos for the Euler-Cauchy equations. And there are the videos for the homogeneous equations with the constant coefficients, and which also include some of the equations of the higher order of homogeneous equations. Okay, and then I discussed a little bit about the Wronskian, which is a test for the independence of the equations, and which may be used for other solutions as well later on. Then in this week, I have uploaded 3 video clips about the non-homogeneous ordinary differential equations. Okay, so that was just a quick review about that. So what we have covered up to now is the up to the non-homogeneous, okay, non-homogeneous ordinary differential equations. Okay, so so maybe you can go through these videos and then try to solve these non-homogeneous ordinary equations as well. So, but if just to recall, so we have the homogeneous case and the non-homogeneous case. So in the homogeneous case, we have this kind of equation: y double prime plus a y prime plus b is equal to by is equal to 0. So for this equation, then what we do is we calculate we determine the characteristic equation m square plus m square plus am plus b is equal to 0. So this is the characteristic equation. So the roots of these characteristic equations determine the type of solution. So if the roots are real roots, so for example, the roots are like real numbers. One of the root is m1 is equal to alpha, and the other root is m2 is equal to beta. Okay, or maybe you can say that the roots are alpha and beta. Okay, so the solution for this homogeneous equation will be c1 e power alpha x plus c2 e power alpha x. Okay, so real distinct roots.
Beta x.
Sorry, beta x, yes. Okay, let me correct it. Where is the eraser? Oh, yeah, here is the eraser. Yeah, it's a beta x. Okay, for drawing. Yeah, beta x. So these are the real distinct roots. Okay, so if, for example, both of the roots are same, m1 is equal to m2 is equal to, say, alpha. So the solution will be y is equal to c1 e power alpha x plus c2 e power alpha x, but both are same. So there will be something added over here. So from the reduction of order method, we can determine that for the second term, we need to add x over here. So that this will be the root. Then this will be the real double root. Okay, real double root. So this will be the solution when there will be the real double roots. And on the other hand, if there are complex roots, especially the complex conjugate rule. So one is plus iota, second is minus iota conjugate root. So for example, those roots will be of the form m1, m1 and m2 will be of this form. It will be of the form alpha plus minus beta I, these type of forms. So then this m1 and m2. Okay, so the solution in this case will be in terms of the cosine and sine functions. So if y is equal to a constant, we can represent that constant a e power alpha, e power alpha cosine of beta x plus b e power alpha sine of beta x. Okay, so this is the summary for the homogeneous case. Yeah, I should write it like homogeneous over here. Yeah, I am rewriting it. So this is the summary for the homogeneous ordinary differential equations. Okay, so with that, we also discussed about the Euler Cauchy equation. So let me add another whiteboard over here. So we discussed about the Euler Cauchy equations. So the Euler Cauchy equation was of the form something like this. It was y double prime plus what was the form of the Euler Cauchy equation?
I think x squared.
It is x squared over here. Yeah, x squared y prime, y double prime plus x, y prime plus y is equal to 0. Okay, this was the form for the Euler Cauchy equation. So the for the Euler Cauchy equation, so let me discuss Euler Cauchy equation later because let me discuss about the non-homogeneous case because that is more recent, and then let's discuss, because Euler Cauchy equation will be a little bit different from the non-homogeneous and homogeneous. Yes, so let's discuss about the non-homogeneous homogeneous ordinary differential equations with the constant coefficients. Okay. So the previous in the previous slide, it was also with the constant coefficients for the homogeneous. Okay, constant coefficients. Okay. So for the non-homogeneous case, so we have this type of equation: y double prime plus a, which is a constant, y prime plus b, which is another constant, y is equal to some function r of x. Okay. So in this case, since this is a non-homogeneous, because r of x is essentially not equal to 0. Okay. Okay. R of x is not equal to 0. So in this case, the solution of this equation will depend on the homogeneous part plus the non-homogeneous part. So so we can say that the total solution, total general solution, will be equal to the homogeneous case solution plus the solution which is related with this non-homogeneous part. So we call it as a particular solution. P for particular. Okay. So this will be the total solution. So homogeneous solution will be determined by the homogeneous method. So in that case, for the y homogeneous, we will consider this equation. Okay, y double prime plus ay prime plus by is equal to 0. Okay, same equation, but with rx is equal to 0. So from this part, we will determine the homogeneous solution by the homogeneous solution method. For yp, solution, so we will use a method which is called as the method of undetermined coefficients. Okay, method of undetermined coefficients, YP. So and the we will be only considering some specific cases of YP depending on the type of Rx. So most cases for Rx involve the exponential function, and polynomial function. So exponential function will be like of this form, alpha e to the power beta x. Okay, and the polynomial will be of this form, like x to the power n, ax to the power n plus bx to the power n minus 1 plus c, and then up to like x to the power 0. That means the constant term. Okay, so it will be, if these coefficients are, if we call these coefficients as with some other symbol. So this polynomial will be like kn plus kn minus 1 and plus k0. So these are the coefficients for this Rx. So that will be the polynomial function. So will be that type. And the third type of function will be the sine cosine functions. Okay, sine or cosine functions. Okay, so we will consider these three types of cases for the function r of x. So yeah, this should be x over here. Okay, so for example, for a function, let me take the example. I'll show you the example. I will not solve it fully, but I can show you over here. So let's take the, first of all, the polynomial case. So suppose that the example is y double prime plus y is equal to 0.001 x square. So this is a non-homogeneous second order differential equation with constant coefficients. And its homogeneous equation is this one, okay? So for this homogeneous equation, the characteristic equation is lambda square plus 1 is equal to 0, okay? So lambda will be equal to plus and minus I, okay? That is plus and minus square root of minus 1. So its homogeneous solution will be then, C1 cosine of x plus C2 sine of x. So you can call these coefficients as A and D or C1 and C2. It's up to you. It is your choice. So, but because for the complex conjugate roots, the solution is in cosine and sine x terms. But its particular solution, yp will be of the form, because this is a polynomial function, okay? Its particular solution will be of the form of a polynomial of, and this polynomial is of a second degree, okay? So for a second degree general polynomial, so we can assume that it will be ax square plus bx plus c, okay? So remember that for this type of method, we assume that the particular solution will be also of the same form, okay? So therefore, since it was a polynomial, so we assumed a polynomial solution over here. So in order to find, because now we know that the particular solution is of this form, so we need to determine the values of A, B, and C, and then we can complete the solution. So for determining the value of values A, B, and C, we will need to compare the coefficients on this differential equation on left and right hand side. So which means that we need to find the y double prime and y values. So yp, and from yp we can determine the value of y prime p. So it will be 2ax plus c, and then it will be the second will be y double prime p. It will be equal to c. Hello.
Oh.
Yes. So did you not notice any mistake?
It should be plus B, not plus C in this first term.
Yeah, I intentionally made this mistake, but I was thinking that someone will tell me. But okay. So whenever I make mistake, you must tell me, okay? 2ax plus, it should be
B.
Yes. And then it should be 2a, okay? So now it is, now we have these values of y double prime and y. So because this is the solution of this differential equation, so we can just input the values of this. So y double prime is 2a, and y is this ax square plus bx plus c. And then this is the left hand side of the equation now, and then the right hand side of the equation is 0.001 x square. So from this we will make the comparison of the coefficients. So if this left hand side has to be equal to on the right hand side, so the coefficient of x square must be equal to this coefficient of x square on the left hand side. So it will, so this means that on the left hand side we have only x square, this value, we have only one term of x square and its coefficient is a. So on the right hand side the coefficient of x square is 0.001. Okay, so in this way we have determined that the value of a is equal to 0.001 0.001. But we need to determine the values of B and C as well. So for this, we need to compare the coefficients of X and X power 0. So there is only one term of X over here. So this means that on the left-hand side, we have B. There is no X on the right-hand side. Okay, so it means that its coefficient is already 0. So B will be 0. And for the second one, the third one, so it is 2A plus C. So these are with without X values, but there is no any term without X value or X power 0. So therefore, this is also equal to 0. So in this, from this third equation, because we know that the value of A is 0.001, so the value of C will be then minus 0.002. So in this way, now we can say that the overall general solution is C1 cosine of X plus C2 sine of X plus AX square. A is 0.001, 0.001 X square, and B was 0. There will be no X term, and the last term is C minus 0.002. So this will be the general solution, okay, of this given differential non-homogeneous differential equation. And if there are any initial value conditions available for us, then we can determine the values of these C1 and C2 as well. Okay. So this was the this case is called as the basic case for the non-homogeneous ordinary differential equation situation. So this is called as the basic case. Yeah. So what is the basic case? In the basic case, any of the solution term for this Rx is not a solution of the homogeneous situation. So that is called as the basic case. What do I mean is that I can explain by the other case. So for example, if this function 0.001 x square, instead of this function, we have some function, something like sine of x. Okay, instead of that sine of x, then the solution of that sine of x will be also in terms of sine and cosine of x. But since sine and cosine of x are already these functions of this horizontal case, then we cannot use simply sine and cosine of x as the solution for the particular. So case, in that case, we will multiply that solution, each of these terms, sine and cosine of x, by x. Okay. So that will be the non-basic case. So in that case, we will use a rule which is called as the modified rule, and that rule is given in the book as well. So for this modification rule, so let's see another example. Okay. So the second solution, second equation is this: y double prime plus 3y prime plus 2.25 y is equal to minus 10 e power minus 1.5 x. Okay, so suppose we have this equation. So we need to determine first the solution of the homogeneous part. So for the homogeneous part, we have this characteristic equation: m square plus 3m plus 2.25 is equal to 0. Please don't be confused. Sometimes I am using for the characteristic equation lambda, sometimes I'm using the symbol as m. So both have same meaning, okay? So in this case, m plus 1.5, this will be the m plus 1.5 square, okay? If you see that m square plus 3m plus 2.25, if you factorize it, then you will get m is equal m plus 1.5 square is equal to 0. So here we will have the situation when we have a double root of minus 1.5. So this is m1 and also this is equal to m2. Okay, m1 and m2 are both equal to this. So in this case, the homogeneous solution will be equal to C1 e power minus 1.5 x plus C2 e power minus 1.5 x. Is it correct?
No.
It should be plus C2x.
Yes, it should be x, okay, minus 1.5x. Thank you for correcting me. Okay, so this will be the solution. But in now we now we look at the particular solution. But for this Rx, which is the term minus 10 is equal to e power minus 1.5x. This has already included this term minus 1.5x, which is part of the solution of the homogeneous equation. So we simply cannot use this term as it is into our solution for the particular part, okay? And since minus 1.5x is not a single solution, it is a double solution for the homogeneous part. So we also cannot simply multiply it by x because x is already here in the solution. So we will have to multiply it by x square in this case, okay? So therefore our assumed yp will be equal to minus 10x square e power minus 1.5 x, okay? So this will be the correct selection. Sorry, not minus 10. It will be, we will assume an undetermined coefficient. Yeah, we will use an undetermined coefficient. So it will be our assumed yp will be an undetermined coefficient. Okay, so remember that. So this will be the correct choice. However, for example, if you will choose like instead of ax square, you choose ax, okay, and then you try to solve it, then you will not get the value of a because the terms on both sides will become 0, 0, 0. Okay, you will definitely not get the value of a. Similarly, without x, you will also not definitely get the value of a. So you will have to choose ax square in the end. So that's why this book says that this is actually a self correcting method. Okay, a self-correcting method, which means that if you make a mistake in the beginning, the method will itself suggest you the correct choice. Okay, so anyway, this is the correct choice that we will make in this situation. Okay, so now we need to determine the value of a. So in this case, there is only one undetermined coefficient. So for this, you will take a first derivative because in this equation, we need the value of the first derivative and we also need the value of the second derivative. So by this approach, so if you will find the value of the first derivative, y3 prime, so it will be, you can make these calculations by yourself, but I have the answer available with me over here. So it will be minus 1.5 ax square e power minus 1.5 x. And then it will be 2ax e power minus 1.5 x. Remember that because this is the product of two functions, so therefore product rule of differentiation will be applied over here. And from here you can find the value of yp double prime. So this will be in three terms. Okay, yp double prime will be, in this case, will be equal to 2.25 ax square e power minus 1.5 x minus 6a x e power minus 1.5 x plus 2a e power minus 1.5 x. Okay, so now we have the values of yp double prime, yp prime, and yp. So we can input into this equation, and then when you will add up these values, many of the terms will cancel out. Okay, I will not show you over here because the expression will become longer and it will take some time to write. So in the end, you will get is this. So on the left hand side, you will get 2a e power minus 1.5 x. Okay, and on the left hand side, you have this value of rx. So minus 10 e power minus 1.5 x. So this will simply give you that 2a is equal to minus 10 and a is equal to minus 5. Okay, so once you determine the value of a, so then you can write the general equation, general solution in terms of this. So it will be C1 plus C2 C1 plus C2x and e power minus 1.5 x minus, so it will be ax square, so it will be minus 5x square e power minus 1.5 x. So you can take e power minus 1.5 x common from those equations. So then you will get C1 plus C2x minus 5x square into e power minus 1.5 x. So this will be the general solution. So again, if you know the initial value condition, so you can apply those values, then you can determine the coefficients C1 and C2 as well. So in this case, then you can see that we have applied a rule which is called as the modification rule. Modification rule. Okay, modification rule. Okay, so what the modification rule says that if any of the term for the solution of yp particular solution are also the solutions of the homogeneous part, then we have to modify it. So you can either multiply it by x or multiply by x square if the root found in the particular part is the double root of the homogeneous part as well. Okay, so remember that if on this side for the homogeneous part, if one of the term is not 1 minus 1.5x, maybe 3x or whatever, depending on the these coefficients, so then you will only use x over here. Okay, or on the other hand, these two are entirely different, so then there is no need to use x over here. Okay, so I hope it is clear. Do you have any question about this modification rule? If you did not understand, then let me know. Hello?
It's okay. We understood.
Okay, then that's good. Then, okay, so then there is now a third rule as well, which is called as the sum rule. Okay, so next example will illustrate the sum rule. Okay, so again, by the sum rule, what do I mean is that, so let's take it with the help of an example again. Suppose if you have a equation y double prime plus 2y prime plus 0.75 plus 0.75 y is equal to, so now that this non-homogeneous term on the right hand side is the term is 2 cosine x minus 0.25 sine x and plus 0.09 x. So now you can see that okay, this is the homogeneous part. Okay, And this is the non-homogeneous, sorry, this is the equation. And then on the right hand side, that is this Rx function is actually the sum of two types of functions. So we take cosine x and sine x as the same type, okay, trigonometric functions. So we have the trigonometric plus a polynomial function of the first degree, okay, in this case. So in this case, the sum rule will apply. So sum rule is very simple. Sum rule will say that the particular solution will be the sum of these two different types, okay. So in this case, then the overall solution will be the homogeneous part solution plus particular part solution 1 plus particular part solution 2, okay. So the homogeneous solution will be in this case, because the equation is like this, m square plus 2y plus 0.75 m square plus 2m. M square plus 2m, that is equal to 0. And the solutions from these equations are, so for example, if you want to simplify it, so it's 0.75, so I can multiply by 4 both sides of the equation, 8m plus 3, and then this will you can verify it, this will factorize into 2m plus 3 and 2m plus 1, okay. So m1 will be equal to minus 3 by 2, m2 will be equal to minus 1 by 2, okay. So the homogeneous part of the solution will be c1 e power minus 3 by 2 x plus c2 e power minus 1 by 2 x, okay. So this is the homogeneous solution. But this now this homogeneous solution has nothing in common on the right hand side. So therefore we don't need to apply the modification rule in this case. The only thing we need to apply is we will assume yp1 as equal to a cosine x plus b sine x, and yp2 we will assume as, can anyone tell what will be used for yp2? I'm asking.
0.09x.
Yeah, but in terms of the undetermined coefficient, cx plus d, okay, not just cx, and then up to, we will go up to the x to the power 0, so it will be cx plus d. So since we have already chosen a and d for this, and then it is for cx plus d. So by the same method for the example 1 and example 2, we can determine the coefficients a and d. And in this case, you will see that the final general solution will be, let me find, where is it? Yeah, the final general solution will be equal to y is equal to the homogeneous solution. So c1 e power minus 3 by 2x plus c2 e power minus 1 by 2x and plus sine x. Why only sine x? Because from the method of undetermined coefficients, you will find that the value of a will be 0. The value of a will be 0. But of course, it is not always the case. It is only in this particular situation that you can say that. So for a general solution, it will be sine x plus sine x, something like this. And for this point 0.09, so the solution will be 0.12x minus 0.32. Okay, so now we have only C1 and C2 are the arbitrary constants. So if we have any initial value conditions, so we can input those initial value conditions over here, and then we can find the value of C1 and C2 as well. Okay, so this was the sum rule. Okay, sum rule. So sum rule is simple. Okay, however, there can be situations when we need to both apply the modification plus sum rule. Okay, as well. So for example, if the for example, if there is anything common. So for example, if these are the functions, and then you get the complex conjugate roots over here. Okay, if you get the complex conjugate roots over here in terms of the cosine x and sine x, then these cosine x and sine x terms will be multiplied by x over here. Okay, or if there is any exponential term with either of these values. So for example, -3/2 or -1/2. So if one of the exponential term over here is e power -3/2, so then that e power -3/2 term will be multiplied by the x. Okay, or for example, in the on this side there is a double root -3/2. And then there is a exponential term with power 3/2. So that e power -3/2 will be multiplied by the what, x or x square. It will be multiplied by the x square. So, yep. Can someone is going to?
No. I said it will be multiplied by x only.
Yeah, if there is a double root, then that will be multiplied by x square. Okay. If there is a single root, then will be multiplied by the x only. Okay. So later on, maybe we will come across some of the questions when where you will have to apply both the modification and the sum rule as well. Of course, modification rule is the sum rule is quite simple. We just have to add up these terms, and then for the modification rule, we have to see that whether there is any commonality from the left hand side and right hand side. Okay, so that's what I wanted to discuss. In fact, I have the third part was like Euler-Cauchy equation. I have already uploaded the videos about that. Maybe you can also have a look at this. So for the Euler-Cauchy equation, the solutions are in this in these terms. So for example, in terms of the, so instead of Euler-Cauchy equation, instead of e power x, you have the solution in terms of the x power n or whatever. Okay, so the only difference is that. Okay, because Euler-Cauchy equations are some special cases of the second order differential equation in non-linear. They are linear, but with non-constant coefficients. Okay, so their solutions are in terms of the x to the power instead of e to the power x. Okay, so otherwise the pattern is the same, but you can see the videos which I have uploaded on this Euler-Cauchy equation on the Moodle. So that's all for I wanted to discuss for today. And regarding the quiz, you have already received my email, so I'm going to retake the quiz now in the next week on Wednesday. Okay. So do you have any questions about this?
No.
No. Okay. Okay. So in that case, any other question about the checking of the assignment? Okay, so if there is no question, then maybe I can